So some terminology that we need to talk about, multiplicity. Okay, this is how many times, how many roots you have at that point. Last year, we talked about a quadratic function like that, and we had that one had two equal real roots. That's what we talked about last year, the quadratics. This year, we're just going to say, okay, that is a quadratic function with a multiplicity of 2 at that point. So if this number is x is equal to 3 where it's touching the x-axis, the equation could be a, which we'll talk about in a minute, x times x minus 3 times x minus 3. It has a multiplicity of 2 at that point. Also going back to our quadratic, these guys here are the roots with a multiplicity of 1. They only show up once. Crossing the x-axis without changing is a root with a multiplicity of 1. It shows up once. This equation might be x plus 4, or a times x plus 4, x minus 2. I said might be. I'm just making numbers up on it. So the multiplicity is basically counting how many roots are at that point. So if we take it to a cubic function like this, each of these guys, each of those ones are the root with a multiplicity of 1. Now, by looking at the equation, what is the degree of each one of those binomials? They're all degree 1. So basically, when I look at this, and you will by the end of the day, okay, we have a cubic function with a positive leading coefficient, happens to be a positive 1 out here, and it has roots at -2, -5, and 3 with a multiplicity of 1. So my sketch, -5, -2, 3. Okay, it's going to cross the x-axis at -2, -5, -2, and then 3. It's just going to go cross. It's not going to do anything fancy at that point. Okay, so if you were to plug that into your graphing calculator, that's what the graph would look like. Crosses at those points. A multiplicity of 2, that's that terminology I used earlier, a two real but equal roots at that point. Okay, so here we have x minus 2, which we're most likely going to write this as x minus 2 squared. Okay, so this is what we think about it. We have a root at +2 with a multiplicity of 2. So they have two real but equal roots at 2, and then another root at -1. So on your graphing calculator, punch this equation into your graphing calculator and sketch just off to the side what that would look like. And then you can sketch this one also. Okay. Did the temperature just suddenly get warm in here? Or I froze for the first period and then I put the hoodie on. Now it's getting warm. you should have got graphs that look something like that for both of those. So when we have, because both of this, we have this guy's got a multiplicity of 2, as do both of those zeros. Again, the fact that I've got it squared up there. How would you describe that point? What did Mrs. Lowy use to describe that where it was just touching the x-axis? The terminology that we need to use is point of tangency. So we can describe this as the turning point is on the x-axis. I'm perfectly happy with that. But the point that we're going, or the terminology that's going to be used throughout is a point of tangency. Although, quite frankly, I leave out the to the x-axis. It's tangent to the x-axis. So the turning point lies on the x-axis when we have a multiplicity of 2. Now, I want you, if you still have that in your calculator, change the powers on those to a power of 4 and compare. What do you see if you change that to a power of 4? Does it essentially look the same, Aurora? It would be definitely more narrow because of the power of 4, but you still have those points of tangency. Now what, and if you were to punch in 6, you would get it even narrower, but you would have points of tangency at those points. What you have there is anytime you have an even multiplicity, you're going to have a point of tangency on the x-axis. So 2, 4, a multiplicity of 2, 4, 6, 8, 10, they're all going to look similar, and that turning point is going to fall on the x-axis. Now, a multiplicity of 3 would be x minus 2, x minus 2, x minus 2. So here we have, again, we have roots. We have a root with a multiplicity of 1, or negative 1, for your x plus 1. And then you have a root with a multiplicity of 3 at positive 2. So again, this would be written x minus 2 cubed, x plus 1. Now, I want you to take a look at, use your technology to graph those, and make a little bit of a sketch, and then see and I've already used the term that I'm going to use, but see what happens at those. Now yours might not be as distinct as what I'm about to draw up here. So you should get shapes that look similar, because again, I'm sketching to that. The one that I want here is this point here. Now, like I said, your graph is not going to be as obvious to it. But what you see there is what's called a point of inflection. We have a point of inflection lying on the x-axis. This is generally, when we get into calculus, we tend to do it a little bit, explain why, but what's happening is it's, hey, I'm going to change direction. No, I'm going to change my mind and I'm going to go back up. Okay. So what we have is this graph is concave down up to a point, and then it becomes concave up. So starting to change its mind, or starting to turn, no, changes its mind, go up. Explaining why, that's a calculus one that we can work with. I'm going to just skip this a bit here because I've already talked about it. If you were to do this, you would find those three would have points of tangency at x is equal to 1 because they are second, fourth, and sixth degree. And then these ones here would have a point of inflection at that point. X is equal to 1. Because, again, we have a third, a fifth. If I was to do a seventh, we would have the same thing. So, basically, we're going to combine all of this into a sketch. Now, there's going to be an infinite number of sketches here, okay, that we could do for this guy. We're just going to get one. We want to know we have a negative leading coefficient. Okay, so that's going to, once we determine our degree, we're going to figure out what the endpoint behavior looks like. We have 1, 0 at -2. It has a multiplicity of 2. Well, that means I've got a point of tangency at that point. We'll keep that in mind when we sketch it. We're at +3 over here with a multiplicity of 1. That means it's just going to cross the x-axis at that point. And we have a third 0 with a multiplicity at 0 with a multiplicity of 3. So that means we have this point of inflection. What do you think the minimum degree for this function is? Or what is the degree for this function? How many roots do I actually have for this function? I have 2 roots at -2. I have 1 root at +3. And I have 3 roots at 0. So number of roots is the multiplicity. So if I've got 2 roots, 1 root, 3 roots, how many roots total do I have? 6. Therefore, this is a 6th degree function. Okay? So it's a 6th degree function, so even numbered function or even degreed function. That means it either opens like this or opens like this. We have a negative leading coefficient, so it's going to open down. We already answered this. This is the 6th degree. So it's going to start down here and down here. We have a point of tangency at -2, a point of inflection at 0, and crossing the x-axis at 1. Again, each one of those things was described to me by the multiplicity. Even multiplicity, point of tangency; odd multiplicity, point of inflection; and odd multiplicity of 3 or higher is point of inflection. Odd or multiplicity of 1 is just crossing at that point. Okay, so here's a graph. It's a sketch. Now, what is one possible equation? Well, we have a root at x minus 2. X is equal to minus, or we have a root at x is equal to minus 2. What's the factor that corresponds to that one? Yes. X plus 2. That's a multiplicity of 2, so I have 2 of them. I'm lazy, I'm going to write squared. X plus 2 times x plus 2. I have a root at positive 3. The factor that corresponds to positive 3 is x minus 3. I only have a multiplicity of 1. Therefore, I'm not going to bother putting in an exponent. And we also have, what's the factor that corresponds to x is equal to 0? Yes? Just x. Convenience sake, I'm going to put it out here because I like mine out front. And it would be x times x times x because I have a multiplicity of 3. I'm lazy, and I'm going to write that as x cubed. That is one possible equation that has that. Remember, there are an infinite number of equations. We could stretch all of them. So I'm going to put an a there to say that we don't have to remember to find that a value if they give us extra information. If you were just graph that with 1x cubed and so forth, you would get a graph that looks something like that if you made it large enough. This way. You're going to be cut off if you use those standard window settings. Okay, so as I said, we gave one possible. We have to figure out the actual for this one. So this is from last year. We have a factored form. We want a factored form. If you guys could help me, and Alexis, what is this number here? Negative. Can't see the depths. Can't see them. We don't know. All right, I'm going to call this point -4 and this point 2. There should be a graph. I don't know why there's no sketch or why I didn't put that there. So, oops, my fault. So, because we have this guy, multiplicity of 1, this polynomial will have, or this quadratic will have a form of x plus 4, x minus 2. Again, we have the roots, the factors that correspond to x, or to minus 4 is the x plus 4. But we haven't found what the a value is. There was another point given to us. In this case, it happens to be the y-intercept. So I'm going to take that third point in this case, and I'm going to plug it in. 16 is our output value. 0 is our input value. Multiplying everything out, a is equal to -2. So any point could have worked except for the 2 that we've already used to do our work. We can't use our x-intercepts again. Any point, I happen to have a y-intercept. So this graph was y is equal to -2, x plus 4, x minus 2. That makes sense, minus, because it's heading down. This is something that you did last year. Because there are an infinite number of graphs that have, or quadratics, that have zeros at -4 and 2. This is the graph that has zeros at -4 and 2 and passes through the point 0, 16. There are no other graphs that do that for quadratics. So you always have to remember that there is an infinite number, and then we have what we want to find. Now, I'm going to say that this is I'm going to say it's -2.5, 0, and 3. This might be a little bit awkward in terms of the fraction, but the process stays the same. We look at this graph. What is the root that corresponds to -2.5? Sorry, what is the factor that corresponds to a root of -2.5? I'll use the fractional form. So I'm just going to set my root equal to, or set my x equal to that root, and make it so now a factor is equal to 0. So we have one factor at 2x plus 5. We have another factor at 0. So we have another 0 at 0. So a factor is x. 2x plus 5 is the third factor, or second factor, and x minus 3 is the third factor. We have a little bit of work to do. What's the multiplicity of -5/2? 3. We have a point of inflection. So I need to cube that guy. What is the multiplicity of 0? Of the 0 at 0? That's crossing the x-axis. It is just 1. So I'll just leave him alone. And we have a point of tangency over here of at 3. So we have 2. Now those are the minimum, because I could also have 5 and I could have 4. But I'm just going to use the minimum version. Now that is a possible equation that has those roots. But there is one more piece of information right here that allows me to find the exact equation. I'm going to put an unknown a in front. We're vertically stretch it, essentially, is what we're doing. We don't want to really get into the horizontal stretching. Well, the horizontal stretching would change the x-axis, so we're always going to vertically stretch it. We have 64 is equal to a times 1, 2 plus 5 cubed, and 1 minus 3. Squared, I should say. So, working this out, we have 64 is equal to a times 343 times 4 My, this is going to be an interesting one. And I would reduce that to a fraction. What's the fraction? (16 over 343), I'm guessing. My final answer. Okay. Now, the reason why that fraction's so weird is because I chose a weird number there. I think if I chosen 2, life would have been a lot easier. The equation that describes this graph with these zeros passing through 1 and 64 is 16 over 343 times x times 2x plus 5 cubed times x minus 3 squared. Have to be able to find that a value. And I said, in this case, I couldn't give you the y-intercept because we already used it as part of our x-intercepts. I had to give you another point. If I'm reading it off a graph, probably the easiest for me to find is the y-intercept. Sometimes maybe not, but that's the one I always look for to begin with. So now we're going to do some matching here. Okay. Now they all have negative leading coefficients. That doesn't help us too much. And I do believe there's a cube missing there. Okay, so if you want to put that cube in above x plus c on number 4. Now, a couple things. A, B, and C are natural numbers. Natural numbers are the counting numbers, 1, 2, 3, 4, 5, 6, positive. Okay? So what we have here is we have x minus a positive number, x plus a positive number. Okay? What side of the y-axis are you going to see a factor that says x plus some positive number? The left side or the right side? We can plug numbers in here. This is going to be 2, that'll be 3. We have x minus 2 squared and x plus 3 squared. I just pulled numbers out of the air. What side is the factor going to be, or the 0 going to be for the factor x plus 3? It's going to be on the left side of the y. This guy's going to be on the left side. This guy will be on the right side. Okay. Our understanding, x minus a negative 3 is what that says, but we don't write it that way. So we have 2 third-degree functions and 2 fourth-degree functions, because the power on those guys is 1 when we don't write it. Which one of these are third-degree functions? A, B, C, or D? Oh, okay. There's 2 of them. Yes. Third-degree functions, A and D, because they're all negative. We start up here and we end down here. That's an odd degree function. Or that's an odd degree function also. Okay? So third is what we're looking for. So when we have these 2 over here, which are third degree, we have a point of tangency on the left side of the axis, and we're crossing the left side of the y-axis. And we have a line crossing here. So which one would this be? We have a point of tangency on the left-hand side. It has to be this one, x plus c squared. So this is graph number 2 because of the zero, or because of the factor telling me this factor lies on the left-hand side. This 2 tells me it's a point of tangency. This one down here by the same process, or process elimination, I guess, but here you have x plus 3 to the power of 1. So on the left-hand side, you have it just crossing the axis. And this is x minus b at a point of tangency. So we're on the right-hand side of the point of tangency, or of the y-axis to use that point of tangency. The same principle applies here. We have a root with a multiplicity of 3. Tells me I have a point of inflection. And the x minus b, x minus 2, that's on the right-hand side of the y-axis. So now we just have to find the point of inflection on the right-hand side. Well, that would be this one here. So this is graph 3, and by process of elimination, graph 4. Pull that right off of the back. That's the type of question, because they're not giving you numbers to plug in. They're giving you variables, although you can plug numbers in if you want, but they won't give that to you on the exam. Now, this is one pulled directly from a diploma. I give you a graph, and I want to know what the y-coordinate is when x is equal to -5. That's way over here, somewhere down here, which is not on our graph. We have 4 points of information. We have 3 zeros, and we have a y-intercept at 0, 5. So that can be used to find our equation, just like we were doing. I'm going to have to use some a value. I want it specific. We have roots at -3, +1, and +5. I'm still not done though. What about the root at +5 is different than the other one? The root has a multiplicity of 2 squared because you have a point of tangency. Now, again, it could also have a multiplicity of 4, but always assume that it's going to be, always assume that we're going to have the lowest multiplicities. We're not going to go 5 and 10. And so there is the equation that would describe the shape of this graph. Here is, okay, so you take your point, your y, in this case, again, your y-intercept, your other point, plug your values in, 5 for y, 0 for x. Oh, we have negative. Nope. Nope, nope, nope. Cubed. (25) times 3, so we have a is equal to, sorry, 5 is equal to -75a, a is equal to -125. We're not quite done the question. We're on that process. Yeah.
Wouldn't it be 115? Would it be 115? Or negative 115?
Here?
Yeah.
25 squared. Or sorry, 5 squared.
I'm gonna do that.
Yeah. Thank you. Yeah, I messed up. I'm dividing by 3. So negative 1 over 15, x plus 3, x minus 1, x plus 5 squared. X minus 5 squared. Messed up somewhere. Doesn't affect our answer. I messed up and put a negative sign in the wrong place, a positive sign in the wrong place. Now, that would be the equation. What is the value of A, this question might read. But what we want to do is we want to know what the y value is when x is equal to negative 5. So we have to go in and substitute. Now you could go ahead and plug this in your calculator and go trace negative 5. Since I don't have a calculator at the moment. We have negative 2 times negative 6 times negative 10 squared. And it's negative. So if you were to multiply that out, you would get the y value for Oh, 1,200 divided by 15 is, you should have gotten negative 8. Okay? So you notice how this, I have one more question that I'm going to do also. You notice how this here goes through the process. Multiple choice question, or sorry, numerical response question that required finding the equation, or finding the general equation, finding the specific equation, finding the answer. Why the diploma for Math 30 is so hard. Now, I want to do one more question. This is not one that can be had put on a diploma. And I know technology is going to make it easy, but what happens when you don't have technology? Well, we can get a general shape of this graph. Can't do anything with the general form, just like I have problems doing much with the general form of a quadratic. The only piece of information, well, two pieces of information that I know here is it crosses at negative 16 and it has end behaviors like that. Other than that, I don't know anything from my general form. So maybe we should take a look and see if we can get something from a factored form. So I'm going to take this cubic and I'm going to perform our factoring on it that we did before. Okay? Because I know what we've done, because I made it up. P at 4, negative 4 is equal to 0. Okay? And again, I like synthetic division. Dividing by this term by x plus 4. So I know the first term of the next guy will be 2x squared. Just drop your 2 down. Add them together, I end up with 7. Negative 28, I end up with negative 4. Positive 16, I end up with 0. The factor x plus 4 is our divisor, our quotient. 2x squared plus 7x minus 4. Now, I know the answer to this, so it's not a big issue. You are either going to have to do explosion method or you're going to have to do trial and error. Okay, so one of the trial and error, I could put a 4 here and a 1 there and see if I can get negative 7 when I do my multiplication. That's 2x minus 1, x plus 4. Again, I knew the answer because I just did it. But a factor, please make sure that you understand that, yes, two numbers that multiply to negative 8 and add to negative 7, or positive 7, are positive 8, negative 1. But the answer is not x minus 8, x plus 1. X times x doesn't give you the 2x that we need here. So I can now sketch this. Already done it over here. I have a point of tangency at negative 4, because I have a multiplicity of 2. And I cross, oops, that was not exactly where I needed to cross. I cross at 1/2. So this sketching part, find your zeros. When you get into it a little bit more with calculus, generally that's the process, is do your long division, find some other stuff. There's other stuff that we do in calculus. Where is the turning point? What's the maximum min or local max, local min, things like that. That's a sketch of a general shape. Again, we can't really test this on a calculator or on a diploma because you have access to the graphing calculator. Okay. There's your homework.